Hello, everybody. We all had a wonderful lunch and a wonderful tour. Thank you, everybody, for joining us again here. Um, we are the science panel, and I have three esteemed researchers and people very active in the field. And you're most welcome to ask us questions and talk with us. I'll start by introducing our panelists, and then we'll talk a few points. Each panelist will introduce themselves and talk about how they're connected to the lunar, to the space heritage, and to the science that related to this interesting topic. And hopefully we'll have a very interesting topic, very interesting panel here. So first I would like to introduce Dr. Brett Denevi. She's a planetary scientist at the Johns Hopkins Applied Physics Laboratory. She is the principal investigator for the Artemis III geology team and is working on cameras and two lunar orbiters, the Lunar Reconnaissance Orbiter Camera on LRO, and ShadowCam on the Korean Pathfinder Lunar Orbiter, as well as two upcoming robotic landers, the Lunar Vertex and the Lunar Vice. Before the moon took over her time, nice bio. She also studied Mercury and asteroids, and you have an asteroid on your name. That's a high point in anyone's career, called asteroid 9026 Denevi. And she served on the steering committee for the most recent Planetary Science and Astrobiology Decadal Survey. Thank you for coming, Brett. Thank you. Next to her is Miss Anne Garrison. Miss Anne Garrison Darrin is the former managing executive of the space exploration sector of the Johns Hopkins University Applied Physics Laboratory. As an aerospace engineer and NASA veteran, she continues as an instructor with the Johns Hopkins University Whiting School of Engineering Graduate Program EP in topics related to space hardware. Together with Dr. Beth O'Leary, Anne authored and edited the Handbook of Space Engineering, Archaeology and Heritage in 2009. This work has been nominated for awards in both the fields of aerospace and archaeology and is a foundational book on understanding of space heritage. Thank you for coming, Anne. Ms. Darrin has been involved in various roles in tens of scientific space missions over the course of her career and brings an engineering perspective to the realm of space heritage. Last but not least, we have Jeff. Hello, Jeff. Jeff is Associate Research Professor of Physics, Department of Physics in Washington University in St. Louis, and the McDonald Center for Space Sciences. Principal investigator for the Interdisciplinary Consortium for Evaluating Volatile Origins, also known as ICE-5O. NASA Solar System Exploration Research Virtual Institute. He has mapped the composition and morphology of the Moon and Mercury as a science team member of 3 NASA missions: Clementine, Lunar Reconnaissance Orbiter Miniature Radio Frequency Team, and Messenger. His lab is there to examine a process known as space weathering, and he uses lasers to replicate the impact of dust-sized particles on the surfaces of these airless bodies. Thank you, everybody, for coming. Very happy to have you here. If you can all just introduce a bit more in depth your scientific interest into lunar space heritage. Thank you.
Okay, I'll go first. Yeah, I have always been interested in lunar geology. I went to graduate school at a time when the moon was not cool. Everyone was on Mars. So I think one of the things I've really loved about the moon is its very ancient history, that it can teach us about the earliest portions of the solar system, especially things like the formation of the Earth-Moon system and giant impact, and how planetary bodies cool, evolve over time, all the way up to the kind of current evolution of the moon, where it's very slow compared to the Earth. That's why it preserves that ancient history. But we're still seeing changes on the surface today with current impacts that garden and overturn the regolith. And so I'm really interested in that aspect of it. As we work on Lunar Reconnaissance Orbiter Camera, we can see of course, the beautiful images of the landing sites. And then we can now, space history is happening, as we saw this morning, every very frequently, the pace right now. So we've been watching different landers, attempts at landing, crash landings, some successful landings, and we can image those both before and after the landing to understand how the surface has changed, which has yielded really interesting kind of scientific insights into how that uppermost surface of the moon evolves over time. And so one of the things I'm interested in as we're looking forward to kind of the future exploration is thinking about how we can best understand the ways that our landing is affecting our exploration and what we can learn. So as we're planning for Artemis 3, for example, we are, of course, the crew will come in on an enormous rocket that will be landing. One of our science objectives is to understand the ancient, possibly preserved ice deposits near the moon's south pole. Those are interesting for a whole variety of reasons, including as a resource potential. But one of the things that we're trying to do now is plan how to best understand how we're actually changing the surface. Water is a byproduct of a LOX methane reaction, so there will be water deposited across the surface. So one of the great things about this mission is that it will allow us to kind of characterize those deposits and best understand how we can plan for future exploration, as well as understanding the ancient ice deposits that we can sample there.
Thank you very much. Anne, would you like to say a few words?
Sure, I'll go next. I'm kind of out of place here because I'm on the engineering side of the house between two scientists. So I have a little different perspective.
We love engineers. It's okay.
Okay.
Couldn't get there without
Heart, yeah.
Yeah. We love engineers.
So I worked with Dr. Beth O'Leary and some others Dr. Peter Capoletti, who does exploration archaeology, and helping to define the idea of getting rid of the giggle factor when you say space archaeology. Not archaeology from space, which is an existing field, but talking about that the material remains in space reflect our society and our culture. And I did the engineering side, how do we get there, how do we stay there, how do we degrade and that sort of thing. But I kind of have an interest in this primarily because I think we should play this little game called Think It Through. And I teach that a little bit. So if we're going to go do something, let's think about it. Let's do it very consciously, because we do trash when we go explore. We know that. We look at our space debris problem right now, which is significant. We also rob. If you've ever listened to some of the extreme sites, from Machu Picchu to Antarctica to Easter Island, we will take away things, borrow things permanently, the Elgin marbles. And so we have the thing about what does this mean, and do we really want to do this? Now, let's make it even more difficult. Today's preservation is all about preserving in situ. Well, in situ, and for example, in low Earth orbit, is a very dangerous place to preserve anything, because it's a potential source of massive space debris, such as the station, such as Hubble Space Telescope, such as non-working Starlinks. They're great when they're working, but they have maneuver ability when they're working. So you have all this in LEO, and thinking about those kinds of things, we can't preserve necessarily in LEO. And by the way, we don't want to preserve everything. That's just absurd. But we do want to preserve certain things, and here we have a super opportunity, especially on the moon, to look at what do we want to preserve. So I just think as we go to do missions, and when you're doing things that are historic, such as the James Webb Space Telescope, or Hubble, which helped us look at the world, the outer space, differently for all of us, that, how do we approach things that are historic? If we decide, which we probably will, to do some sort of interplanetary, intersolar system kind of a mission, that's historic. And how do we think about it, and where are we going to go with it? So with that, I'll hand it over to a scientist and get off the engineering side.
Thanks. So I am really happy to be here. I got my started in the legacy of Apollo, really dreaming of space and thought I'd be an astronomer, and then I realized astronomy is not what I want. It's geology, and I accidentally took a geology course and learned about rocks, and that was great. And then learned that you could study rocks on other planets and the moon, and I thought, oh, this is perfect. It's at the great intersection of science, sci-fi, astronomy, even astrology. And it really got hooked. And for the first part of my career, I was studying Apollo samples and using them to correlate with remote sensing data. The surface area of the moon is roughly the surface area of North and South America combined. So imagine trying to characterize the geology of an area that big from 6 sample locations. It's near impossible. You learn a lot, but you can't learn everything. So to be able to expand beyond those locations, we use remote sensing data to take the chemistries from those sites to extrapolate through the moon globally. But there was this persistent problem, this thing called space weathering, which changes nice, fresh, rocky material into dark gray, lacking any kind of mineralogic information to it. And it's called space weathering. And what that is a combination of micrometeorites that hit the moon because there's no atmosphere. For us on Earth, we get meteor showers, nice, brilliant streams of light that happen as these little dust-sized grain enter our atmosphere at hypervelocity, 20 kilometers per second. On the moon, they just hit the surface, and they change the regolith, the soil, from something that has mineral information to just kind of glassy slag. But in there's even important information, because as it changes the chemistry, some of that chemistry might get released to form some of the volatile deposits that we've been studying at the South Pole of the moon. The other part of space weathering is the solar wind, which is protons from the sun or hydrogen from the sun streaming out and irradiating the surface of the moon and changing it with time. So for the last 10 years or so, I've been studying how those processes change the surface of asteroids, Mercury, and the moon, and what kind of information we can learn from that process by doing experiments in my lab with lasers, as Reut said, where we can't accelerate small particles very fast, but we can use laser light and short pulses to actually replicate that deposition of energy by micrometeorites. So with that, I'll give it back to you.
Yeah, thank you very much. So I'll say a few words about myself as well. My name is Reut. I'm an astrobiologist by training. I worked on stromatolites in Shark Bay in Western Australia, and then I moved into other extreme environments like hot, slightly radioactive hot springs, and a lot of like hypersalinity and hyper-arid areas, especially in the south of Israel, in the Negev and in the Dead Sea. And most recently, I was a scientific advisor for the Weizmann Institute for an astrobiology mission to Europa in the planetary science department. And at the moment, I left my academic positions and went into the industry. And I'm currently CSO and co-founder of a company called Starstone. And we're dealing with biocement and disrupting the construction and concrete industry. What interests me about the moon and about the science that we can do there as an astrobiologist, everything that has to do with the molecular science, DNA, everything that life forms might have left behind, I'm very interested. We have stuff on the moon that for 50 years, we don't know what changed, what exactly changed, whether it's materialistic or chemicals, or whether it's the biological components that were left behind. And for that, at the moment, we don't have any remote sensing capabilities to do it. So for instance, if I were in charge of a scientific mission that would have these different types of science that you have to do on the moon, and specifically in different Apollo sites, I would definitely support a human and remote sensing joint mission. I wouldn't go just for remote sensing, and I would say, yes, it is worth the lives of astronauts, and I would make sure that they are well trained in life sciences as well as other things. Moving forward, Brett, would you like to tell us a little bit about these photos that we're seeing?
Oh, yeah, sure. Actually, if you can just go no, one more, yeah.
Okay.
Yeah, so this is the Apollo 15 site. We saw similar images this morning. These are from the Lunar Reconnaissance Orbiter camera that has imaged all these sites from orbit at about 50 centimeters per pixel. We can see that most of the flags are still standing based on watching their shadows kind of move around throughout the day. One of the things we've learned, actually not necessarily from the Apollo sites, because we don't have a perfect before landing comparison, but from some of the subsequent landers, we've imaged basically the entire moon at this point. And so we've able to compare exactly a before image to an after image. And so that includes the Chang'e landers. There was just the Intuitive Machines mission, even some of the missions that have crashed. We see how those missions have changed the surface. You can measure how far out the blast zones affected the surface. So for some of these more recent landers, it's a couple hundred meters where you can see the surface has changed. And so understanding that change is just interesting for this conversation here of, how close would you want to land? I think you definitely would not want to get too close, but roving is not going to affect the surface here. And so I think, scientifically, one of the interesting things we have here is an event that has changed the surface, and we know the exact time it has changed the surface. And the images, for example, of the boot prints, those weren't taken just because they're cool. They were also taken for scientific and engineering purposes to understand the geotechnical properties of that regolith. How does it compress? How does it, how do the walls of those little boot prints hold up? And so I would love, of course, to go back and see how those have changed over time, because throughout the Lunar Reconnaissance Orbiter's mission, another thing we have been imaging changes is impact craters. We've seen hundreds of new impact craters that have formed on the surface, and we can pinpoint their dates as well because we have the before images. So I think that's a kind of case where maybe scientifically it would be very interesting to go to an Apollo site for that. But you could also go to one of these new impact craters as well and do a whole other kind of really exciting science study. I love hearing Jack Schmidt's words shared this morning too, that of course he did a phenomenal job sampling the Apollo 17 site. As Jeff mentioned, the time there was limited. They had 3 EVAs and about 7 hours for each EVA. They, it was a phenomenally complex site as well. So that geologic history that we've spent over 50 years now looking at those samples, trying to piece it together, if I were going to go back to an Apollo site, it would not necessarily be to look at some of these kinds of surface changes, things that people have affected the surface. I would definitely want to go back and re-explore that Apollo 17 site now with all of the new questions we've learned from those samples and the ones that we have not been able to answer. It landed just inside the rim of an enormous impact basin, the Sorek-Abramovich impact basin, and we still have not confirmed for sure whether the rocks that we went there to collect, in fact, date the age of that basin to about 3.94 billion years old, or if they are from contamination from somewhere else. So while I love these kinds of questions too, going back, being able to go back and explore just the moon's geology itself, having been there already, would be, definitely worthwhile.
And definitely complex from a logistics point of view. Absolutely. As an environmental microbiologist, the time that you are outside is very precious, and if you're doing it with a 150 kilos spacesuit, even though on the moon it's going to weigh a lot less, obviously, but you have problems with communications, you have time on your oxygen tank, so yeah, it's a big issue. So I'm guessing rovers can probably help out a little bit, carrying some stuff around. Yeah, yes, let's see what else we have here. Tranquility Base in the surroundings, so this is also very pretty.
I don't think this is mine.
No, I think this is Anne. Anne, are you?
Yeah.
Yeah. You want one back or one?
Well, the Tranquility Base. Let's go to the next one, talking about the things that are there.
Excellent.
And
So
this is just a big list of the inventory of what's up there.
it's a shortened list, actually. It's a short list.
Yeah, I was just
Thank
trying
you,
to
Anne.
give you a sense of everything that's up there on the ground.
Amazing.
And it's everything from poop to working materials. So, of course, we think about what we could learn from these, what happened with the space weathering, which
Right.
would include what's happened with solar wind, micrometeorites, the radiation environment, et cetera, and, of course, the human remains. But this is what's up on the Tranquility. I think I have another slide up there.
Yeah.
Let's see. Oh, that's the different, I think, was that yours or mine?
Not mine.
Okay, that's mine. The different bases. And do I have one more after that, the different sites? Yeah, okay, there's going to be one more after that. These are the different sites. And what I want to point out here on these sites, and this was done by Dr. Peter Capoletti from Penn State, Abington, is potential keep-away zones. We talked about keep-away zones or off-limit zones or areas we might want to protect. These are the ones that have, everything isn't necessarily historic, everything doesn't have to be preserved necessarily, but you need to actually be able to select a few things and say, hey, this was the first, or there was something really significant about it. So that was a pretty interesting slide. I just thought I would show you that as to bring in that balance of looking at and protecting.
How many sites are we thinking now on the moon that needs to be like protected for scientific integrity and analysis?
Well, no, there's different things. Scientific integrity, or you want to talk about historic preservation, or because it's historically significant. Those are different. We may be protecting different sites for different reasons.
Right.
So this one just shows 5, and that was more for the historical significance. Okay.
Okay. Do you want to, Jeff? Do you want to go for your take on the moon?
Your stake on the moon?
My stake on the moon.
Yeah.
So just to reiterate, there's the moon that we're used to seeing. The near side of the moon is always pointed towards us, and the surface area of just that one side is smaller than the surface area of the United States. You, I'm sure, have heard in the news a lot about water at the ice, or water or ice at the poles of the moon, and that's because the lunar north and south pole are at this unique spin rotation, where, because if it was a perfect sphere, you just have a straight line between night and day. But because there are craters, of course, on the moon, any craters in the polar regions actually don't see any sunlight. The sunlight just shoots right over them. So they're staring off into just space and equilibrating their temperature with deep space, which is 3 degrees Kelvin. So the temperature of these permanently shadowed regions, those blue spots on the top, or lower than 100 Kelvin in temperature. So water molecules that bounce around on the moon, or any kind of gas that bounce around on the moon, when they fall into these permanently shadowed regions, they lose all of their kinetic energy and they become trapped for geologically long periods of time. And the debate is, where did this water and other volatiles come from? On the bottom there, you see a neutron spectrometer map of where there's hydrogen, and we infer from the hydrogen map that that's water. And we think the most likely sources are external, either from asteroids or comets. Comets are about 50% water ice, as well as CO2 ice. Asteroids have some percentage of water in them too, so they would be delivering water to the moon, much like they may have delivered our water here at Earth. It's one of those things even we don't know for Earth. Where did we get our oceans of water? So by looking at the moon and looking at the ice at the poles, we might be able to understand where the sources of water come from. And then the other two sources, one is solar wind, as I mentioned before. Protons or hydrogen streaming out from the sun will get implanted into the rocky material on the moon, and the rocky material is by weight about 50% oxygen. So when micrometeorites hit the moon, they allow that combination of hydrogen and oxygen to actually recombine. If you've ever done electrolysis with some water in a battery, same thing. And that water molecule may bounce around and find the cold traps. Or that bottom one is a volcano on the moon. Just like here on Earth, when volcanoes erupt, they bring up volatiles from the deep mantle, one of which is water. And what we might be actually sampling is ancient water from the inside of the moon, which also tells us, because the moon formed from Earth, we think, that the Earth actually had a lot of water early on. So when the moon formed, it took some of that water with it. So again, we can use the moon as a witness plate for where Earth may have got its water from external sources, or whether it formed with the water itself.
That's very, very nice. Thank you very much. So if I wanted to sort of like learn about the composition of the water and everything, aside from the remote sensing, what kind of like equipment or scientific technique would I need to have on the moon in order to do that analysis, for instance?
So the CLIPS missions, there's one coming up, Viper, and it's scheduled to launch, I believe, the end of this year. And it might get delayed a little bit. And it has two instruments on it. One is a neutron spectrometer. So it's going to be driving, it's going to land at the South Pole and be driving in and out of these permanently shadowed regions and taking measurements. One of it will be the neutron spectrometer looking for hydrogen. The other is NIRVIS, which is an infrared spectrometer. So the lights, it's got headlights on it, because it's driving around and permanently shadowed. You got to bring the light with you. It'll actually heat up some of that surface and see if it outgasses any potentially water, CO2 ice, methane, ammonia ice, all of those. So be able to break down the molecular structure based on spectroscopy.
Yeah, spectroscopy is really good. Like we're using it in different environments, and we have been really good at automating the whole sequence of it and getting the data back, whether we do it on Mars or on the moon. We've got really good at it. Is there going to be some issues of contaminations, do you think, or something like that?
One of the things we do worry about, again, these are cold traps. Anything that gets into it sticks in it. So if you land nearby with a rocket motor that's, of course, expelling hydrogen and oxygen, basically that's what they use for burning, it could contaminate some of that signature. So it is something we have to think about, but hopefully, we can move away from that blast zone, as Brett was saying, and get into, pure material. But it's something to think about for preservation. If we want to go there to, we're going to use isotopes to measure where the water is coming from. If we go there with rockets who are filled with Earth terrestrial isotope D to H ratios or oxygen ratios, it's going to contaminate our signal, and we won't get a pure representation of the material. We need to be aware of sources of contamination that could happen with rocket fuel.
And we can also, though, work to mitigate those in the ways we investigate too. There's water thought to be buried deep, so if we can, scrape off that top layer of terrestrial contamination, do drive tubes below that, you can start to get at some of the deeper water. So I just sometimes worry that the contamination story almost prevents us from going and doing some of the exploration. And there are so many things that you absolutely have to be there to learn, and including, I think that's one of the ones that's not really feasible remotely. And it's not everything is even feasible with, a robotic in situ instrumentation. It's something where we will want to go and sample the material, bring it home, and have, many terrestrial laboratories studying this question. And so I think there are ways to mitigate the potential for contamination too.
Thank you. Anne, would you like to add something?
Go up against a scientist?
Of course. You're an engineer.
No,
That's
but
what you do.
but they
we
do
can't do that.
Well, they do bring the idea that there's going to be a tension between the exploration, and I want to also bring in a word here today, exploitation of the cislunar environment, the cislunar economy. It's not just exploration, it's the potential exploitation, which is there's business and commercial interest and during the different nations, and that tension between preserving some things but allowing for the space. If we tell Brett and Jeff, you can't go there and look at that stuff because it's precious, they're not going to like me very much. We got to figure out how to make that balance of sites that are okay, sites that aren't, things that we can have our own science labs up there.
And how are you feeling about allowing international research organization taking samples from Apollo sites and other which are very U.S.
If we decide, and we talked about the Apollo sites,
right?
That's one thing. But I think international scientific collaboration is utmost for coming up to decide what we're going to work on and where we're going to work and where the labs on the surface and where the mining and that kind of thing. Without international collaboration, I love the earlier policy talks because the United States has been so amazing at setting standards and working with others to set standards around the world. Mm-hmm. That's part of exploring the cislunar economy is bureaucracy. If we don't have rules of the road, that's rules of the road for how we do our management. How do we do our RF management, our spectrum allocation management? How do we manage the limited resources we have up there? So it's a little bit of a bureaucracy that's part of our savior. And that includes spec standards and that kind of thing. Agreements.
I'm just wondering who would be the organization to do all that, coordination and making the final decision, and how long the process is going to take, because we're expecting, dozens and dozens of launches to the moon in the next decade. So who's going to talk to these people and these companies who are coming from different, different countries and tell them that's okay, that's not okay? Who do you feel
the Outer Space Treaty started it, but, the Artemis
Mm-hmm.
Accords has gone a long way.
Yeah.
We're at least bringing everybody's attention up there.
Yeah.
Yeah.
Okay.
I
Yes.
was just going to add too, I think there are always opportunities for, science to collaborate with industry and with all of the commercial exploration that is going on. It's also a huge opportunity for science. Nobody is going to give me, $100 billion or something to go and collect my samples. But when you're building up a kind of broader lunar ecosystem, as long as it is done thoughtfully, science is included, even in an example like mining, there's incredible opportunities for science. And, geologists love road cuts on Earth. That's where you go. You look at all the rocks exposed. No geology funding is going to go and make that road cut for you. But it presents an opportunity that's come through, other kinds of
Actually, that's a
industry.
great allegory, is the road cuts here on terrestrially. That here we have a commercial entity that could, and if they do it thoughtfully so that you can get your samples and that kind of activity. It's a good one.
Thank you. So before we go to questions from the audience, I just wanted to ask Jeff, for instance, do you have any message to the next generation of space explorers, especially for the private and the commercial sector? From a scientist's point of view, what would you like to ask?
It's not actually maybe so much from a scientist's perspective, but to be inclusive. It's a word we are getting to learn. We've seen what Apollo looked like, and what the typical mission and astronaut looked like then versus now, and it's becoming more inclusive. But it's also being considerate of multiple cultures, thinking about how sometimes we might be using the moon as a cemetery. It's great for that one or two people who can afford to have their ashes, smashed into the moon. But, what about everyone else who might see it, differently from a different perspective? And in trying to actually have a community that considers these different perspectives, and to not just go forth and, kind of claim, this area is mine for the water, kind of if you've seen For All Mankind. There's a lot of inter-country tension because of the water. That's something that's going to have to be worked out.
It happens on Earth as well when
And
you
it
have
happens-
limited
yeah, we see it.
resources, and sweet water is a limited
Yeah.
resources in some areas, absolutely.
And the far side of the moon, as
Yeah.
far as being in a radio quiet zone, and that's another resource for radio science that needs to be considered. So in going forward, being open-minded and creating a dialogue, and not just going for the science, thinking about other impacts that it may have, either for the science or for planting a flag.
Thank you very much. Anne, would you like to?
I'll go right along with that. I thought that was a great little wrap up there.
Right.
That we just need to think about what we're doing as we do it, and I think we have to be careful. We know about the remains shooting remains onto the moon. We have certain populations that see this as a very holy place, and they don't appreciate your bones or my bones up there. We do have to be inclusive and bring people in and figure out exactly what we're doing. So we're very thoughtful about it. I think that's important.
I think there were a time in archaeology on Earth that nobody really cared about the endemic population, and then they had this whole shift of how you talk with the local people and respect their customs. So I think you're thinking in that kind of a direction
Well,
also about
it's
the moon.
actually always too little, too late.
Right, right.
And
We
certainly,
learn. I know we're just scientists, but we learn. That's fine. Yeah.
And I thought Anne was going to include sustainability. Like, if you're landing something on the moon and leaving it there, why not make it something useful for the next group that comes?
Right.
Yeah, that's great. Okay, so thank you very much. Brett, do you want to add something, or you're good?
No, I'll add on that sustainability. I love the Artemis kind of mantra of sustainability, and all the aspects, especially the sustainability of exploration and making sure we can kind of make these longer term plans for the science and exploration.
Okay, thank you very much. Does people in the crowd have questions for us? We will be happy to answer. Yes. Just raise your hand. He has the microphone. Thank you.
Hi. Oh, is it on? Oh, okay. Hi. So I know a lot of the talks today, we've talked a lot about the importance of storytelling, people, heritage, culture, in preserving space. And I was wondering, because a lot of us have been inspired by the Apollo missions, by sci-fi, and for me, the stars themselves. But unfortunately, like 80 to 90% of the US and Europe live underneath light polluted skies. And so I was just wondering how y'all see light pollution, like mitigation, and light pollution, just like, I guess, policy. So anybody could really answer this. But the role of light pollution in preserving our space heritage. I don't know if I worded that well.
I think you've just reinforced our point of, if we're going to do something, think it through, because we're already seeing we may have passed the tipping point on light pollution when we get up into the constellations we have in low Leo right now. We have 5 major companies at least that have major constellations up there, contributing greatly to the light pollution. And the next generation, the second generation of Starlings, helped dose it a little bit, get it down. But had we thought about it ahead of time and said, hey, this is going to be a real problem at some point, when you start seeing constellations of 12,000, 32,000, this is real. And so I think that this is the real point about having things like this and thinking things before we go and do things, and seeing if we should have put some restrictions in place, because once they're up there, we've passed that tipping point, I think.
I was wondering about like ground-based light pollution too, if anybody had any thoughts.
Okay, good luck.
Yeah. No, so I actually have a bit of experience in that. I used to work in Martesh Ramon, which is a night sky reserve now, due to the local. So usually what happens when you want to get like a night reservation, so you won't have light pollution, what the issue is to get as many as local organization under one roof. So this was like 6 years in the making, and it included the local municipality, the local nature reserve organization, the locals themselves that they wanted, and everybody had to pull through. So for instance, the engineering of the local municipality didn't know anything about how to prevent light pollution in the first place. And then he went and studied and basically realized that if you change certain types of LEDs, for instance, for street lighting, then you can you can make them much more direct to the spot beneath them, and then you get a lot less light pollution. But it took several years to get all these different organizations under one roof and into that sort of like way. But they had, it also was in their own interest. First of all, it's a beautiful spot, and there's a lot of astronomy done there. There's a WISE observatory for the Tel Aviv University, but also it's part of the local life tourist industry. They do astronomy tours. So if you have an area which have these different interests coming together, then you can lower the light pollution, and you can initiate these processes in order to get all the engineering solutions that you need. On the ground-based, I'm not talking about Starlink. Unfortunately, I have no pool there. So that's about ground pollution. That's from my experience. So you can gather the community together, and you can gather the organization, and then you can make it happen. And it's not that an expensive thing to do, actually, changing a few lights, doing the right, engineering solutions, and so on and so forth. And now it's a source of pride for the local community. So it's a great success story. Thank you. Thanks. Yeah.
So I think we're all aligned about preserving unique historical sites and locations and equipment and so forth. The 2011 guidelines prioritize Apollo 11 and Apollo 17 as first and last. What I haven't heard from the scientific standpoint is the scientific value of going back to the biological deposits that were left. We've got 6 sites to choose from. Are there any discussions that leave out Apollo 11 and Apollo 17? But there's 4 others. Is there any discussion about the accessing the scientific value of the left behind biology?
That's a great question. I'll have to look into that more in depth. We definitely want to go back to the biology samples and what was left behind. We can learn a lot about how life may adapt or may have even survived some of the conditions. And we can learn, and that's actually really important as a practical implementations for the next missions, that if you have human crews. So, and if you have life support system and you integrate them, so it's actually a really important aspect that's not being done enough. And I would argue even having like a sample return mission would be actually very beneficial. And sometimes you don't even have to bring the issue with sample return, because you know it because of the astrobiology decadal and everything like that. But basically, when you have a sample return mission, there's a lot of issues about the cost versus why would we go and have the sample return come back. And when it comes to, for instance, finding microorganism on Mars, eventually it was decided that we do need to do this sample return because the cost of all the equipment and techniques and methodologies that you need in order to ascertain that this rock actually has a remnants of a life form, it's a full list of a lot of equipment that you cannot sustain on a rover, on a robotic mission, on a spaceship or anything. So if we're taking it to the moon, which is much more closer, I would argue that you can do a sample return of a very good selection of the biological samples. You can bring it back even to the ISS. You don't have to be worried about, cross-contamination to planet Earth if you're really worried about mutations happening over the years and over the moon. And you can have, using the laboratory equipment that we have on the ISS. And also the astronaut corps has much more now scientists, which are trained. They didn't have any scientists trained in life sciences at all. They had physicians and they had other people, but they didn't. Now they have much more people who are into life sciences, whether it's the DNA, RNA, whether it's tissue engineering, I don't know, things like that. So we can do sample return mission from the moon if we want to take care of those samples. It will be eventually, I think, more cost efficient than actually sending another crew there to look into the samples. And I don't know yet how to do it, but from an engineering point of view, sending a robotic mission to to pick up those stuff, it's not easy at all. So that's for engineers to answer. Anne, thank you.
A lot to be said for robots.
Yeah, thank you.
Thanks. This is a question for Brett. Where are we at with the science of PSIs, plume surface interaction? How much uncertainty is there around these kinds of issues? And should we be prioritizing either experiments or engineering data or something to kind of wrap our minds around it? So it's one thing if the human landing system lands once, but it's a far other thing if we imagine the cislunar economy actually gets to this place where people are taking off and landing all the time, right? Maybe something that happens with just one landing is very different than where you have 50 landings a year or something that could impact these kinds of sites if there is global circulation of this dust. So I'm curious your thoughts of where we are, where we need to go, and what we might need to prioritize in terms of PSI.
Yeah, I mean, we are prioritizing it, and there will be a lot of data that comes back in the next few years. The thing. There are, dedicated, cameras observing that can do very high-speed motion, watching all of this as they're landing. The only part that I do worry about there is that because a lot of these upcoming missions are commercial landers and they're very concerned about proprietary information, I don't know what extent all the data will become, publicly available, able to study. And so I think that is on, NASA and others to make sure that as these companies are under contract, part of the data return that they're getting from that contract includes things like plume surface interaction. And there'll definitely be a ton of natural experiments coming up, and the uncrewed Starship demo will be a prime one there. But making sure that data is available for all to learn from is going to be the key. And I actually don't know the status of all of those different agreements that must be worked out.
Yeah, I also like to add that in parallel, we need to figure dust mitigation, like powder mitigation, dust mitigation techniques that we are employing already on planet Earth, but it's a completely different issue on the moon. But basically, you do have techniques to do that dust mitigation. So it's true that we're going to do plumes, but we might be able to enforce using certain techniques to make that plume go down again pretty easy. Thank you. Next.
Hi, thank you. It's been really interesting to hear about the science and the information that can be, the information that we can get from the surface of the moon. So I'm an objects conservator with Lisa, and in our profession, we agree to abide by a code of ethics, which includes preservation of scientific investigation, or the ability to be able to do that. So, so for example, like we prefer not to add any materials, and we want to preserve things as they are. So it's interesting to hear from the other side, which is scientists thinking about preservation of sites. And we do have a lot of parallels with that in archaeology and heritage preservation, like has been touched on a bit. So yeah, I hope that we can keep working on these things together.
Yeah, absolutely. That's a great point. So in archaeology, usually have a bit more findings. Like you have this set of stuff that you find in a site, and you first catalog, right? You catalog, you map, you digitize everything, you do a whole list. And then you have this priority list of what you can take to destructive kind of tests, right? If I want to check and do DNA extractions from some samples, then that sample is not going to be preserved at all. So I think there is room for having already like a line out of saying how you approach this kind of a site and take completely analogs from an archaeological sites, which have also very precious, you're looking at a Neolithic burial site. Everything is very fragile and very precious. So I think it's a great idea to work together in order to understand how to do the science stuff. Because so far we just go to planetary places, right? And we just pick stuff up and we measure them. We think about it as a materialistic science. But here, it's getting into a completely different niche. So thank you.
Yeah, I totally agree, especially when you think about the scientific priorities, but there are, some things that might be worth disrupting a site for, and how do we decide what those are? And not every site can be, or even when it comes down to an individual sample, like a rock, it can't be everything to every kind of investigation. So how are you going to prioritize what you want to do and what you want to preserve?
Yeah, and it sounds like that might come up at some point with the Apollo landing sites, because if they're being slowly destroyed by micrometeorite impacts and plumes, then at some point maybe we do want to go there and remove things so that we do have them preserved. So it would be interesting to see how quickly they are damaged by the environment of the lunar surface.
So we have some, yeah, go ahead.
I was just going to say, quickly to a geologist is like 100,000 years. So,
yeah, thank you. No, that's great. Anyone else? Or Shira, are we good? Yeah. Okay. So thank you very much. Oh, there's one over there. Yes.
Hi, Jack Corelli with the Planetary Society. Something that I often think about in regards to space science and exploration is engagement with the public. How can preserving these historic sites, both on the moon and looking at Mars, where we've also landed multiple rovers and landers, how can that help educate the public about, how can we help educate the public about the importance of science in space exploration? And also on the converse, how can the public then get involved in these efforts to preserve historic sites?
Well, I'm going to jump in on that one because we talked a little bit about, you have to do dust mitigation. There's going to have to be habitats. There's going to have to be shelters, that kind of activity. To do manufacturing, assembly, anything on the moon, we're going to have to be concerned about the regolith and the dust. But, we live in a world where we're really maturing virtual reality. And you don't want to be in the situation where the only two people that get to tour the Apollo landing sites are Bezos and Musk. But, and I just said that out loud, didn't I? So anyway, you don't want to be so elitist. And so one of the things that we have with beautiful virtual reality is the ability to do immersive things and to be able to have a repeat of an Apollo landing site so people can explore here on Earth and that. And I think as we're starting to use that more and more in education purposes and that, and in museums and the immersive and that, I think we have great opportunities. Because frankly, we're not all going to Mars unless you want to get fried with radiation. You know, there's a great way to send a robot. You can send things, you can explore, you can teach, you can learn, but we can do it with virtual reality or augmented reality. So I think we've got opportunities here.
And I'd like to add to that too. You know, Brian this morning said, you know, for historians and curators, their job is to look at the artifacts and tell you how it got there, why it's important. As scientists, you know, we get paid by NASA. You know, it comes from taxpayers' money. Our job as scientists is to tell you why this rock is important, how it fits into not only telling us about the moon, but our place in space, why Earth is the way it is. You know, we study moon because it's actually like studying a history of what happened in this Earth-Moon space 4 billion to 2.5 billion years ago. That record has been erased here largely because of plate tectonics and erosion. So to understand that early history of what went on, we have to look at places like the moon and asteroids. And it is our job as scientists is to relay that story to the public, and that's why we're here in part today.
Yeah, and from my own perspective is that if you do analog missions and you take teenagers to analog missions, they completely get how to do science in the field. They finally understand what it means to pick up a rock and how to describe it and what kind of testing you need to do. And if you are able to do like even a tiny bit of space simulation missions, then you got like your whole next generation with you. And if you combine it with what Anne said, and you have these virtual sessions as well, and you have the knowledge from NASA passing through, then you get the full package. And it's great. And they love it. So thank you very much.
Thank you.
Thank you all.
Thanks.